Hello, my friends. It seems that I'm online. It's the fourth part of the seems to be seemingly never-ending active scope probe 2 GHz bandwidth design live stream using KiCad. Part 4. Last time we finished the schematic, and today our goal is to work on component layout and PCB layout, hopefully. If you were here last time, you saw me importing the picture of the original PCB. You were seeing me imported the PCB shape taken from the I think original drawing, which is on GitHub. The link to the project is running on the bottom edge of the screen, as you can see. And today we can start with the component layout. There will be some changes in the PCB layout, but still, thing number one, I don't feel like copying the entire layout because we have made some changes. And the second thing is that some components were changed. We will not use the tantalum capacitors. We will use slightly different SMA connector. I think this design uses the 𝗏/SMA. I think I placed a normal SMA to the 90 degrees angle, right angle SMA. Frankly, I am still not sure what's the best, if this long wave guide or to place the SMA as close as possible to the op amp. This is why I used the right angle SMA. This is the component that allows me to place the SMA like here. And the circular part, not the circular, the cylindrical part of the SMA connector will be like 5 millimeters above the surface of the PCB, which can bring an advantage of a short waveguide plus we can use not only right angle, we can use straight SMA, which is, I don't know if it's an advantage or not. I have a news. The last time I found a Mac, I don't know the name of the company, Mac something car, I think. The spring-loaded sharp tip. If you were there, you can recall, I hope. So I immediately after the show, I sent them an email or a message from their website with the question, who is the supplier for or distributor for the Europe, for the EU. And they immediately responded that unfortunately there is no distributor for Europe, and they are not able /willing /happy /anything to send me anything from the US here to Europe. We didn't discuss any tariffs. I'm just joking. Never mind. It means that the spring-loaded sharp tip, as I found last time, is not applicable for our design, because even in 2026 you can't buy it. So I will leave, instead of the spring-loaded sharp tip, only a soldering pad, as we discussed last time. And when the first prototype is working, I will find something that is easier to buy, and maybe make some changes on the PCB, because frankly, I don't have a spectral analyzer or VNA to check the bandwidth of the thing, so I can only stimulate it with some high frequency output of my functional generator, which is limited to 100 megahertz, but the amplitude of the generator is not same as at 1K, for instance, so I can verify only the function, not the gain at the high frequency, etc. But yeah, it's too soon to think about testing, because we still don't have anything but the schematic. So let's roll our sleeves up and start. I will use, for the starters, with the split screen. I will start with the split screen because yeah, I need to separate the components into groups for comfortable component placement, etc. So there is a big group of the high frequency amplifier with, yeah, basically the entire area here is this block. The SMA connector is not included in that group. Never mind. So if you select all the symbols in the schematic editor and then switch to the footprint editor and press P, which is a shortcut to pack and move footprints function. So P, KiCad collects all the footprints into a compact group, and it can help with the component placement. There is the dual LDO, which is somewhere near the charge pump. I think here is the thing. The original design have two tantalum capacitors, as you can see, the yellow ones, but we replace them with a regular capacitors made from ceramics, because the datasheet of the LDO says that the ceramics is recommended. I think the footprint will be somehow compatible, so if it doesn't work, for instance, if there is yeah, I don't know what can happen, some instability with of the output voltage of the VCC or VEE, so we can change the ceramics switch the ceramics to the tantalum, which has some important parameters are different. For instance, the equivalent series resistance is higher than for ceramics, or the voltage rating is lower than for ceramics. So yeah, some other things, but not only improvements are on the tantalum. As you can see, as you know, tantalums are not ideal, as well as ceramics. Each of them has its pros and cons. Let's continue with the component placement. There is the barrel TC connector with the Schottky diode. You can easily identify the placement is here. And what's resting here is the charge pump IC, which is here. This one. This is the charge pump. This is the LDO. This is one of the op-amps, and this is the high frequency op-amp. And the last component is the SMA, and soldering pads. Soldering pads are here. I think I added. Yeah. There was a question from the last time of the shielding, I think, or there was a question about shielding. So I added these soldering pads that can be placed on some spots near the top and bottom edge of the PCB, like spare pads for, I don't know, metal case, cover, shielding, you name it. And here will be the SMA. We can place it like here, or we can place it here. Frankly, I don't mind placing it here, but we have to count it with, because the LDO component placement should count with the position of the SMA. At least we have to keep the space below the cylindrical part of the SMA to allow comfortable mounting of the cable. We will see. So here is the thing, and we can start. The PCB edge is the yellow line, and I will use the same strategy as always, so to take as little space as possible. Here is the Schottky diode of the original design. We have the SOT 123, I think. Yes, SOD 123. So yeah, like this. The charge pump. So this capacitor should be placed as close as possible to the input voltage. Input voltage entry point is pad number 9. So this pad is input voltage. What we can do and what we should do is to check the recommended component placement. Yeah. This is here, and this is a note about sharing. So is there a recommended PCB layout? Here. Here is the pin number 1 with the big capacitor as close as possible with multiple grounding vias. Here is the switching capacitor, or I don't know how they call it. Here is the RT, which is I don't know what it is. We have direct connection to ground, RT. Let me check. I can't remember. What is the function of the RT? Input connection for programming the switching frequency. Okay. If the RT pin is tied to ground, the switching frequency defaults to a fixed 500 kHz. So in my opinion, we can change it because to have comfort of changing the switching frequency can be beneficial. And I think there is not so crowded, like the area is not so crowded that we can't place a 0603 resistor. So yeah, small change. I think it's a good step to have the flexibility of changing the switching frequency. If not, the 0 ohm resistor costs like nothing, and yeah, I feel I'm doing the correct design thing. So here, yeah, back to the data sheet. There is the example of the basically nothing special. Both input and output capacitors are close as possible to the IC, as well as the switching floating capacitor, and the RT is as well as possible, as close as possible to the pin, and the entire IC is placed on the grounded polygon. That's what we definitely will do. So here is the switching eight and 5, okay. The switching capacitor is here. Yeah, the center of the IC can be aligned with the center of the cap. Let me check comments. No comment, perfect. Not perfect. I wish you drop some comments, but if there is no comment, I can freely continue without any interruptions, which is good as well for you. Okay, I think this position is what we want. Negative output capacitor. Yeah, I will align. I'm aligning it with the input capacitor. And finally the RT, which leads from pin number 2 to the ground. Pin number 2 is here. They use like 0402 or even smaller. I can see what's the problem. Yeah. The 11 is mode, yeah. The mode is 11. This position, yeah, number 4. This position should be better for us. I think we can. Yeah, I understand. Maybe I will use this strategy because here is power entry and the polygon will be easy to draw and will be like thick and almost straight like hockey stick, and here this capacitor can be closed, can be placed like here with the short distance to the output pin number 4. The output can be in the bottom layer or in the inner layers or even at the top because there is plenty of space. I think the original design uses, yeah, you can see, yeah. There is a ground polygon here, and yeah, it will be good. So continue. Let's continue. No test points, which is probably fine because the capacitors are quite big, and yeah, we don't need special test points here. Now the dual LDO. Pin number 1 is power entry. There must be this capacitor, and pin number 5 is negative power entry, and there must be this capacitor. Texas Instruments always have PCB layout examples or recommendations in their data sheets. Layout guidelines this time only. No, this is so they use positive input polygon connecting the enable as well. The negative input polygon, here is the noise reduction capacitor. Grounds, all caps are grounded to the thermal exposed pad. So the inputs of the IC is number 1 and number 5. So here the positive is number number 1, so we need to rotate it. Here is the power entry. So here is like the bulk capacitor, and here is the ceramics. Okay. Can be input positive, input negative, output positive, output negative. Yeah, the number 1 is here. Okay, there will be a lot of tracks on the bottom. Never mind. So input ceramics. Output ceramics is here. Okay. And now the negative capacitor for the input. Let me check the layers. Okay. Yeah, there is a. Okay, I will keep it. I will keep the fabrication layer displayed. It's fine. Noise reduction cap, according to the data sheet, close to the pin number 3, and the ground is directly to the bottom pad. So here, yeah, the ground will be connected. Here will be the big polygon. So yeah, something like this. Here is the bunch of other components, some resistors. This is the feedback network. So we have positive feedback network, which is this capacitor, this resistor, and this resistor will be connected between pins 10, 9, and the ground. So near the pin 9, this is, as you can see here. So I will place it. This is like working position, not the final position. So don't get me too seriously. I am preparing the spot for each group. Preparing spots for each group. Here. Yeah. So between pin 10 and 9, these are two. I don't know what I did. I don't know what I did. Cap, resistor close to the IC, close to the IC package, and then capacitor. And here is the upper, no, the lower side resistor with the ground pads here. So here is the upper VCC and feedback. Here is the cap, and here is the bottom cap. The same for the negative side. We have to keep the buffer line. So yeah, this is like the ideal position, I think. Cap. No, this isn't cap. It is cap. Here is the bottom. This way. Yes. The output is 6. Okay. It seems that the original design has the polygon with the cap here connecting, and the original design placed the capacitors close to the IC, while the datasheet says that the resistor should be close to the IC. Never mind. And let me check the original schematic. No, this one. The big bulk capacitors are on V plus and V minus. No, VCC. Here are the big ones. VCC and VEE. Okay, so not directly at output. Okay, maybe I did. No, VCC is pin number 10 and VEE. Hey, see, here is a mistake. My mistake. The output number 6. Yeah, number 6 is output. I connected the wrong spot of the network. Here is the output. Naturally. Yeah, it was strange that the capacitor here was connecting to the feedback network, and this is what I didn't understand. Yeah, that was a mistake. Here is the output negative, here is output positive. This is how it should look like. But of course, not only the symbol, but the capacitor as well. So I have to rearrange the network a little. No. The power flag will be still needed. I will place it here. So negative output pin number 6, symbol of the VEE is here. Here is the bulk capacitor, the feedback network for the negative, and the VCC is directly at the pin number 10, which is positive output. Here is the positive feedback network. Here is the big capacitor at VCC and the LED. Okay, now it should work. Yes, exactly. So we have placed components for the power supplies. The original design placed the capacitors like further from the IC, but I want to use the same strategy by connecting both ground pads directly with the thermal exposed pad of the IC. I think this composition is too far from the IC. You can see that here are the grounding vias on this side, because the line on the package of the tantalum capacitor marks the positive side, so negative side is here. Here is the ground side, and the input capacitor is here, directly on the ground pad, which is good, but this is not, I think, optimal, as well as the caps are like switched with the resistors. And our design now more reflects the requirements of the IC, of the datasheet. I always respect the requirements of the datasheet. Now we can move the entire group closer here while making or creating space for the SMA here, at least the design flexibility. You know what? I will place the SMA on the proposed position, but after I change the footprint. Why? Because as you can see, the SMA is well above the the surface of the PCB only part which should be marked with or surrounded with the cartridge rectangle is the big base part, not the entire thing. This is what will reflect the real situation. Here. Yes. Not good. As you can see, the capacitor is too close to the cylindrical part. It will not work. So I think I will place the SMA here. Now we have two possibilities. Either place the SMA there as I placed right now and design the long waveguide, or to use a different coaxial connector. We can use MMXC, like that one. We can use UF.L. We can have SMA as we have right now. BNC is out of the discussion because it's too big. Yeah. Okay. The smallest one is the UF.L, but it needs very thin coaxial cable and it's not so robust. So it would be ideal to use like a short piggyback with the UF.L on one side and SMA on the other side, and place the SMA on the panel, like the back panel of the enclosure here. Okay, I left 2 millimeters from here, from the like base wall of the SMA to here, to have some space for the enclosure. Yeah, let's continue. Let's continue. So we have the op-amps. Our trimmer is bigger. Not so much. Okay. We have the coupling capacitors near the pin 1. Let's check the data sheet. It's Texas. It means there should be some good design example. Layout. This is schematic example, layout example. I don't like it. Pin number 1. It's awful example, frankly. Let's check pin number 1. VS is the positive supply connection for the input stage. And VSO is output stage. Okay. What do we need more? What I mean, there are two 100 and one capacitor of the 10 nanofarads. So I'm asking, where should be the battery of 2 and where should be the single one? Let's check it. Minimize the distance between the power supply pins and the coupling capacitors, of course. Place the high frequency capacitors close to the supply pins and on the same side of the PCB, okay? Place larger capacitors further, okay? Yes. The separation of the input and output minimize the therefore connect supply pins to the input and output is the same potential. Maintain separate individual copper capacitors for all supply pins. Okay, so let's continue. Power supply bypass capacitors. Low inductance, LICC, to minimize high frequency impedance between the buff and the bypass capacitors. The layout is completely C. In the entire datasheet, they call it VS plus and VSO plus, like supply for the input stage and supply for the output stage. No, the example schematic uses the symbols with the VCC and VCC2. I will place the 10 nanofarad capacitor to the output stage. Near pin number 12. The original design uses LICC, but I found that the impedance of the LICC is not so ideal as it looks like, and this capacitor has a lower impedance, even though. And this one will be for the input stage near pin number 1. Oh, this one. Okay, so there are 2 pairs, 4 pairs. Okay. These capacitors will be close to the pin number 8, which is this one. From pin number 14. As you can see, somebody is calling me all the time. Let's make a short break. I will be back in a second. So we can continue. I found out that that phone number from the Spain was some PCB agent from China. And I didn't pick up the phone. They started me messaging on WhatsApp, so I blocked them. These guys know how to sell. As you can see, I am now placing the input network resistors. The easier way would be to open the original design and to copy the placement of the components, but I think there is not so many of them, and I think I managed to do that. Now I'm working on the bigger op amp. Here is the network. Components should be placed here. So this is the feedback from pin number 6 to pin number 2. Not so easy. I should use my brain instead of copying the design, but it's so intriguing to. Okay, here is the capacitor near the pin number 4 of the high speed one. Pin number 4. I don't know where to place them. Pick and place, mechanical, group assembly. R11 is here. R11 is here. Okay, RF out, it makes sense. R12 is here. C2 is here. C15, R15 is here. C3 is here. Okay, there is a okay. We have the LED, which can be placed, for instance, here. Or somewhere else, for instance, here. I would like to keep this area with the compact copper pore. With the label here. Okay. Now the soldering pins. Yeah, I think it was better to open the assembly because I was lost at the moment, and now I'm pretty sure I did it correctly. as we said. There can be some shielding. I don't know if it will happen, but at least we can make some preparation work for it. Yeah, it mixes with the capacitor of the power supply. This is the output one. This is the RT. Okay. We will see. Okay. So the components are placed. How it looks. It looks good. I think I will work on the PCB layout next week because I feel like I don't have much good energy in me. I think it's good. I think it's good for today. And next time we will finally finish this design. So part number 5 next week. I don't have much time yet today, so yeah. Thank you for being here. There is no comments, so it doesn't matter, but no comments, so no questions. See you next week. Thank you for being here. I feel tired, so next week it will be better. We did a good job, placed all components. The design is prepared for the PCB layout. This is our design. See you next week. Bye.